great pleasure that I introduce Harry Jones to give today's talk about magnetic fields for physics and other things. Some of you will know that Harry co-supervised my PhD back in the medieval period. He's done an enormous amount of work in high magnetic fields, particularly in basic studies of applied superconductivity. Also, and I guess more of his time has been spent doing this in the last few years on the development and engineering of pulse field magnets and the development of high field magnets. In fact, it was Harry and Fritz Herwach who together took a lead role in developing the copper steel materials that have been used to produce the highest fields. I don't know whether the highest fields in Europe, but depends how you measure it.
Various competing stories.
There are competing stories in terms of duration and pulse field, but certainly Harry pioneered this composite conductor, which has played such an important role in the now widespread use of pulse fields throughout Europe. Harry's not a conventional scientist. His academic route he can explain if he feels he has to for himself, but suffice it to say that in the last year or so, Oxford had the good sense to finally make him a professor of condensed matter physics. So it's with great pleasure that I introduce Harry talking about magnetic fields for physics and other things.
Thank you very much, Damien, for the generous introduction. And Damien's quite right, we go back forever and ever. Every now and again he reminds me when I perhaps question the way he's going to do something, and he can always come back with the sharp retort, well, that's what you told me to do all 6 years ago. So. Right, just get a few things out of the way. I'm getting to that sort of stage in life, and somewhere like Oxford, you can give yourself all sorts of fancy titles. And the one I forgot about until I put this slide together on Monday is that I am in fact the director of the Nicholas Curti Magnetic Field Laboratory, which is something we put together with Wolfson Foundation money about 8 to 10 years ago now. And it's basically a pulse magnetic field facility, but it also contains, for example, a 21 Tesla superconducting magnet and a couple of other magnet systems. I noticed a lot of the audience are gratifyingly young. But I also know that when the young people see 40 years, and actually it's 45 years, if I'm really going to do it, they're sort of feeling of dread comes over them, and I know the way they feel, because some years ago a colleague, very distinguished colleague of mine, I won't mention his name, was celebrating, and someone I'm very fond of, but was celebrating his 80th birthday, and we had a dinner at, I think it was at Wolfson College, and he did like his history. And as we drove home at sometime just after midnight, my wife said to me, oh God, it was 10 past 11 and we were still only on 1947. Well, I hope I'm not going to slip into that trap of dwelling too much on the past for the past's sake. But at the end of the day, I have sort of seen it all. I've seen it come and go. And if you can always tell I've been in this game 40 years because I never know how to work one of these things. Here we go, 1964. I was a young, I actually started, Damien referred to my unorthodox background. I actually started life as a student apprentice with the Atomic Energy Authority at the Atomic Energy Research Establishment at Harwell. And one of my first placements was with the MHD section, magnetic hydrodynamic section of the direct conversion group. And prophetically, one of my jobs, I had a very junior role, of course, but the various jobs I had, let me just explain what this is. This is basically a huge night storage heater. It's full of alumina pebbles. I think there are 11 kilowatts of crucialite elements in there. And we used to warm this thing up over a period of days, if not weeks. And then behind this wall here, there's a bank of argon cylinders. And we used to blast the argon through the heated alumina pebbles through this section, which here is just a pipe, but normally would have a very elaborate duct, an MHD duct with electrodes on it and so on. And this, though it may not look much like it, is a magnet. It's a split iron cored electromagnet, and it's on a little railway thing, so we could slide the poles of the magnet around the MHD duct. So you got a hot gas which used to be seeded with potassium, and that was my job as well. I used to distill potassium, believe it or not, to get it pure. And we'd blast the hot gas through there. The whole thing would be over in 2 or 3 minutes. It would take weeks to get ready for a run. It would last 2 or 3 minutes. No computers in those days. We had a UV, multi-channel UV recorder to get the response we needed in the time. 24 channels, I think it was. And we could put paper through it at the rate of 120 inches a second. Believe that, 12 feet a second, in order to get the time resolution as well. No computers. Anyway, I was in charge of this. There was a little generator next door, motor generator set, which used to generate a couple of Tesla or so across the duct of the magnet. So, fast forward for 40 years, and what am I doing? I'm still working on MHD. This is an MHD magnet. It's made of high temperature superconductors, which we've certainly never known, even thought about in 1964. And this time it's the opposite effect. In one case we're a generator, in this case we're a motor. And I don't know if you've seen the film The Hunt for Red October with Sean Connery and what have you, but the whole idea is that you generate a magnetic field in here. You have electrodes that put water, current through the salt water, seawater, and you get a force that drives the boat along, and here it is in a large pool of salt water that actually at Culham. This is a teaching company scheme thing. So in a way it's an illustration of me still being in the business, still doing more or less the same thing but with very different materials after 40 years. Right, so how do we generate high magnetic fields? I've sort of started this by saying that leaving permanent magnets to one side. Well, permanent magnets are actually pretty useful these days, and they've improved exponentially in the last decade or two. But nevertheless, you're talking even the very best materials, you're talking about a Tesla, if you're lucky, the surface of a neodymium boron iron magnet. As a little aside, of course, if you think about what you can do with bulk high temperature superconductors, the ITCOs of this world, you can trap flux in them, and you can actually have permanent magnets of around the 15 Tesla level. I think the record stands at now. Slight inconvenience, you've got to have them fairly cold, but nevertheless it is a sort of permanent magnet. But leaving that aside, we've really got to look for electromagnetism to help us get to our high fields. Well, I've divided these into various categories. Non-destructive, well, I should put in brackets after that, we hope, but the idea is they don't destroy themselves. And I perhaps should have mentioned here, having shown that very first slide of the black and white 1964 magnet at Harwell, I should have perhaps mentioned iron cored electromagnets, because they're the classical laboratory electromagnet. But of course, the trouble with iron, it tends to saturate at around about the couple of Tesla level. So if I was going to put under 1964 and 2009, I'd probably have to put 2 Tesla, and in 2009, 2 Tesla again. Because to get to any higher than about a couple of Tesla using iron can be done, and there have been magnets built, the famous Bellevue magnet in Paris, for example, which with highly tapered poles something the size of a railway carriage, you could generate, I think it was up to 3.5, 4 Tesla, something of that order. But in general, a couple of Tesla, and it's more efficient to chuck the iron away and rely on air-cored solenoids. Of course, the powers involved are considerably greater. So classical magnets to me are multi-megawatts, and I mean multi. I had a little setup of very modest 2 megawatts at one time until the health and safety executive took an unhealthy interest in it and we had to shut it down. But I'll tell you in a minute, put it in some sort of context, probably 10, 20, 30, 40 megawatts, this sort of order. And now we're looking at, I think in Tallahassee, you'll hear me refer to Tallahassee a lot. For those of you who don't know what that is, it's the National High Magnetic Field Laboratory in Tallahassee, Florida, where they have something like 40 megawatts. It's the biggest magnet lab in the world, and they have something like 40 megawatts available. And they can generate around 35 Tesla just using, I'm going to say copper, it's a bit more complicated than that, and a lot of water cooling. You know, many, many cubic meters of deionized water, because these are all bare conductors, an hour. Low temperature superconductors were a real boon. I've got an eminent predecessor in my job. His name is Martin Wood, or Sir Martin Wood as he is now. He spun off the Oxford Instrument Company in 1959 from Oxford University, and he was one of the first people to make modest superconducting magnets in the 1960s of around the 5 Tesla level. Now we're sitting at around 23 Tesla using just low temperature superconductors alone in windings working in liquid helium. Hybrids, which are classical water-cooled magnets plus usually low temperature superconductors, and again Tallahassee for example, they have 45 Tesla. It's the largest hybrid magnet in the world. I can boast to have the first working hybrid magnet in the world because the concept was invented in Oxford by Wood and Montgomery, which was about 16 Tesla, but this was something like the mid-1970s. High temperature superconductors, again, I always claim I was responsible for the first serious high temperature superconducting magnets, certainly in this country, and probably in Europe, and I've just shown you one of them. Now, the problem with them is that, we'll talk about the problem with them a bit later on, but if you hybridize them with a low temperature superconducting magnet or a classic water-cooled magnet, fields of around about the 28 Tesla level have just been generated, and there are serious programs to generate 30 Tesla using HTS magnets. I should really have another category here. These with the little blue asterisk are all continuous. You turn them on and hopefully you generate the field forever. If you call from here on down discontinuous or semi-continuous, we're getting into the so-called pulse regime, where for anything of the order of 1 to the order of a second, you can generate a pulse of field. And I'll explain later why we bother to do that. Then you can use what I call semi-destructive, where 1 turn of copper, you put a lot of electrical energy into that turn, and it actually blows up. But before it blows up, and with the plasma created at the rupture of the copper, you still get a huge current, and therefore can generate a very big field of the order of microseconds, a couple of microseconds, and fields of up to 300 Tesla have been produced at places like Michael von Altenberg's lab in Berlin and Mura's lab in Tokyo. Then we get to the destructive bit, and this is the bit I like, and I should have brought the picture to show you and I've forgotten, I'm sorry. But what you do here is you take magnetic flux, which you generate from perhaps a superconducting magnet or just an ordinary copper thing, just a few Tesla, and then you very briefly compress it. with a liner which has a low magnetic diffusivity. So for just briefly, it contains the flux lines while it's being imploded, either electromagnetically or, and the really fun bit is, you pack TNT around the liner and you press the handle, detonator goes off, and very, very briefly you can generate of the order of thousands of Tesla. I put 2 Tesla there because there's an argument. The Russians claim to have done 2,400 Tesla. Fritz Herlach says people have only really done things in 1,000 Tesla, but of course you have to write very quickly if you're taking data because everything is destroyed. You sample, the experiment, and what have you. But serious physics are done in these flux compressed and high explosive fields. Well, you'll know this, of course. Most experimentation, I've just been looking around at Damien's very impressive laboratory where he's got more solenoid magnets than you can shake a stick at. And we've been discussing, you know, getting into fields with different geometries and different temperatures and what have you. But most experimentation is done in the bores of solenoid magnets. Now, it's difficult to get across to people that the magnet bore is very expensive real estate. If you just think about classical magnets, water-cooled magnets, for a given field, the power required goes as the cube of the bore. This is the so-called Montgomery convention where he always puts the bore radius as calls it A1. 30 Tesla in a 40 millimeter bore, you need about 20 megawatts. If you just go out to 50 millimeters, you pretty well double that. And practically, you can only do that in Tallahassee. Most people just don't have that capability. For superconducting magnets, you use the same, and this is the volume term in here, where you've got resistivity functions and the current density. And the volume term still applies to a superconducting magnet. Superconductors are very expensive. So the volume of a superconducting magnet, and therefore the cost, goes as A1 cubed again. Well, practical limitations. For classical magnets, making a sweeping statement, it's really heat that kills you. The superconducting magnets and the intrinsic properties of the superconductor, but in a way, it's heat there as well. It's once they go normal, you have got a heat problem, and you've got helium boiling off and what have you. And this is down to the critical magnetic fields and the critical current densities. So those are some of the limitations on the kind of level of field you can get to for experimentation. I guess the main message of what I'm going to say today is that we're kind of running up against the buffers a little bit, unless there are some, I hate the word, but unless there are some breakthroughs. I mean, this, for example, is how you can improve the cooling in a bitter magnet. For those of you who don't know what a bitter magnet is, it's a bitter plate is a plate of, I'll say copper. Well, they always say a sign of madness is the ability to draw a perfect circle, so I'm obviously all right. And that has in it, that would be the bore of the magnet, and it has in it a radial split, like that. And what you do, you form a thick helix. Can I draw this? Probably not. But you get what I mean. You get like a thick helix with several of these plates on top of one another, insulated in between and only touching for electrical purposes at the slip. So you end up with this very thick helix, but you have to push water cooling through there, so you do it through holes. And what's actually happened is over the years, because these things date back to the 1930s, the idea, but over the years, incremental improvements have been made on the shape and position of the cooling holes, from the simple round hole distribution here to the what's called the Florida bitter magnet, because it was developed in Tallahassee. And that's probably given us, I don't know, 20% improvement in the sort of field we can get from these magnets. You're not going to get orders of magnitude improvement at this stage. You're going to just do a little bit better each time. In the case of superconductors, we're looking at the critical properties, improvement in critical properties. And now, these days we're talking about so-called 2G or second generation superconductor, which consists of a very thin film of yttrium, barium, copper oxide on a highly textured substrate, and very impressive intrinsic current densities can be achieved with these materials. But the problem is, the engineering current density, which is what really matters in magnet construction, is the law of diminishing returns soon sets in when you have to introduce steel strip to reinforce the conductor, for reasons I'm going to go into in a moment. So, if we have a little think about these critical properties, this is a highly simplified diagram of the critical properties of two families of superconductors. There's the low temperature superconductors, which arguably have been around since 1911, because it's only in 2 years' time we'll be celebrating the 100th anniversary of the discovery of superconductors. And what you can see here, that with the low temperature superconductors, you hit the field axis at around about the 25 Tesla level. Again, sweeping generalizations here. And you hit the temperature axis at around about 20 Kelvin. Now, with the high temperature superconductors, and this is why everybody got so excited in 1986 when Bednorz and Muller discovered them, we've got the situation where they hit the temperature axis at really around about 100K, and they hit the field axis again at around about 100 Tesla. I'm keeping things very simple. But this is where I'm going to cite Jones's theorem, or Jones's axiom, whatever you want to call it, which has never let me down. And it says, the higher the temperature the superconductor works at, the more impossible it is to use. And it's never let me down yet. Even the low temperature superconductors, you talk about friendly old niobium titanium that you bind body scanner magnets out of and work in liquid helium. It's lovely ductile material. You can jump on it, you can tie knots in it, do anything you like. It's cheap and it works very well. But it's only good for 10 Tesla, it's only good for about 10 Kelvin. Niobium tin, which is the next only other real contender as a low temperature superconductor, goes to 18 Kelvin and probably 20 odd Tesla. But it's a pain. You have to heat it after the magnet's been wound, you have to use refractory insulators, you have to handle it with extreme care because it's very brittle, and so on. But believe me, it's a pussycat compared to these things, where the material, you are basically making magnets out of teacups. That's what you're doing. And they're as fragile as teacups, and they're as intractable as teacups. But nevertheless, strides are being made, and what happens is, and this data is a little bit elderly now, but I like to show it because I took it. But again, coming up against the buffers thing, nothing here is going to have improved very much in the 6 years or whatever it is since we put this together. But what it does illustrate is that if you look at niobium titanium, logarithmic by the way, this scale, and you look at niobium tin, they take some beating down at this field regime in terms of engineering current density. They are orders of magnitude better. This is a high temperature superconductor that we all got excited about in 1986 because it works in liquid nitrogen. That's 77 Kelvin. But you see, it's pathetic. it collapses. The critical current density collapses in even a small magnetic field. However, as you take the high temperature superconductor back down to low temperatures, here, whatever that is, that's probably 4 Kelvin, liquid helium, suddenly we see that at this sort of level, we're in business. So that's why I talked earlier about the hybridizing of high temperature superconductors with low temperature superconductors to get to really quite high fields. People are aiming at 30 Tesla. Because we'll see in a minute, there's another problem which we've got to overcome if we really are going to go to these much higher fields. And the other limitation, the other problem, is stress, basically. Now, what I've tried to show here as simply as possible, and probably tried to oversimplify it, is this is a cross-section through a finite winding, a finite solenoid winding. And I've represented that by just 3 turns at the ends, at the middle, the centroid, and at the other end. And what we see is we're generating a magnetic field, as you all know, which looks like this, and we're carrying a current, I, and what we remember from, is it Fleming's left-hand rule? I can never remember somebody's left or right-hand rule. We remember that there's a force orthogonal to both field and current. And in this setup, what you get is there are three stresses we have to worry about. I'm going to put forces on. Strictly speaking, I should have put sigmas rather than F's. There's the radial stress, so this loop is being pushed out in this direction, which causes a azimuthal or hoop stress. And then, where the field lines are going off the parallel with the axis, you get a component which gives you a stress in the axial direction, which comes from either end. Imagine a lot more turns there, and that builds up to a maximum on the centroid turn of the magnet, on the mid-plane of the magnet. So the general effect is a barreling. Now, to a point you can live with that. It's a lot more complicated than I've shown here. If these really were free windings, what would actually happen is these would open up at this point, and then they'd, at what we call alpha over 2, in other words, roughly halfway through the windings, the outer layers start to reinforce the inner layers. But because we do funny things like inject impregnate with epoxy resin and so on, you actually get a very funny composite structure. So forces out here can actually pull the turns, the inner turns, out with it. So the overall effect is that, and eventually you get failure, usually about there. Not always, but usually about there. Bearing in mind we might be using extremely high voltages, extremely high currents, and we always start at low temperatures. We always start at least liquid nitrogen, in the case of a pulse magnet, to increase the thermal capacity of the magnet. And so at 60 Tesla, you'll find, because this is the sort of level of fields we want to be looking at now, you'll find that the bursting stress is somewhere in the order of 20,000 atmospheres. So what do we do about that? Well, there's one way around it. And if you've got infinite power, infinite space, infinite money, you can get infinite Teslas. So supposing we wanted 100 Tesla, and we only wanted to use soft copper, we didn't use them, for our winding, nothing more sophisticated. And say we wanted a very modest bore of 20 millimeters. Well, using the constant stress pattern, and the constant stress pattern is this. The hoop stress in a turn, so the hoop stress is given by BJR, where R is the radius of the winding, B is the field it's experienced, and J is the current density. So you can see that as you go out, the hoop stress goes up, but the field goes down. So you can find some level of current density, in other words, you can change the size of the conductor so that the stress is always constant. So you can, in principle, build a magnet where the stress is always below the elastic limit of the conductor. Well, you can do the sums for that, and you find that if you did that, 20 millimeters bore, you'd then have an outer diameter of 20 kilometers. And the power needed would be 1 million megawatts. And that, as I put there, is, I'm sorry, this slide is a little bit Oxford-centric, but that is the power put out by Didcot Power Station, which is the local big power station to Oxford. For cooling, and this is a silly guess because I've got no idea, you probably need the contents of the North Sea per day. You wouldn't use salt water, of course, if you had any sense, because we're looking at a highly big vault here and what have you. But nevertheless, this is the sort of thing we're talking about. However, if we use a strong conductor, for example, some steel reinforced copper, the outer diameter would come down to only 4 meters, and we'd only need a miserable 2,000 megawatts. That's only one Didcot. And perhaps reroute, again, I apologise for the Oxford centricity, we'd reroute the Charwell, which is a tributary of the Thames that goes through Oxford, through the magnet. So it's all getting a bit silly. But if we were to restrict ourselves to a short burst of field, say tie up Didcot for just 1 second, then we're in with a chance of getting there. No active cooling needed for a start, if we could rely on an adiabatic process. The temperature of the magnet would go up, but we could go away and have a cup of tea, wait for it to cool down again, and then have another go. But we can't always do that, as you'll see shortly. In practice, what is likely to happen, and what is happening in Los Alamos and in the European Consortium ARMS, something I'm very pleased about because I actually coordinated that, is a long-time constant outer pulse magnet to give a platform field of, say, 60 Tesla, and then superimpose on that a short burst of much higher field. So, by going to pulse fields, we lose the heat problem, but not the stress problem. So how do we combat the stress problem? Well, we can use strong conductor to wind the coils. As I showed you, if you use a strong conductor, you come down from 20 kilometers, for example, down to 4 meters for your magnet size. And the trouble is, though, that strong materials, for example steel, which has an ultimate tensile strength of the order of 2 gigapascals, it can do, has a poor conductivity. It's only about 2% of the international anneal copper standard. Copper is 100% IACS. But copper is weak. It's got an ultimate tensile strength of about 300 megapascal if you're lucky. Well, our answer, as Damien alluded to earlier, is to combine the two. What we've got here is a very cheap and cheerful idea. We take something like a 304L stainless steel, preferably a high nitrogen steel, and you then co-draw that with copper inside it. The drawing is important because what you do is you draw it to a very, very high level of cold work in order to get the very, very high strength you need. Now, I alluded to ARMS earlier, where ARMS stands for Advanced Research Magnet Systems, and what we did there is we built a big outer magnet from copper steel, the conductor I've just shown you, and we made a small inner magnet from something else. I'll talk about that shortly. And by a long, lazy pulse on the outer magnet, which is something like this, something that big, with a hole like that in the middle, we generated around the 40 Tesla level, and then at the correct moment, we pulsed the little inner coil, and we achieved Well, we did achieve 80 Tesla. I'm very pleased with this thing. I was very pleased I managed to lead the program, led it through some troubles. I sort of got mentioned in dispatches at Brussels and so on. But one of the things I'm very proud of, we did condensed matter physics in fields above 75 Tesla, non-destructively, for the first time. And that's what we did by this coil X, coil in, or outsert, insert, depending which part of the world you come from. And that's just a little schematic which shows you a large outer magnet powered by a slow but very energetic capacitor bank, and a small inner magnet powered by a fast bank. So we've got coil in, coil X. Well, that little inner coil was actually made by a very interesting technique, which I'll explain in just a second. But there are alternatives to the copper steel. There are exotic microcomposites such as copper silver, copper niobium. And these have strengths that defy the rule of mixtures. In other words, with so much copper and so much niobium, you only ought to get a strength of whatever. But what these things do, and in the case of copper niobium, niobium is immiscible in copper in the melted stage and precipitates out as dendrites. So if you then take it and draw it down mercilessly, rebundle it, draw it down again and so on, the dendrites come out into very fine whiskers, and what they do is they pin dislocation movement in the copper matrix. So you get a much stronger material than you ought to do, and yet at the same time you get a fairly good conductivity. Problem is, they're very expensive. I mean, a good example, just recently I was quoted 26,000 euros for just 300 meters of a conductor I wanted to get hold of. Another way, and this was pioneered by my friends in the Catholic University of Leuven in Belgium, and that's to wind high-strength fibres into the magnet. And I think you get the idea of this. As you wind, you can, if you have a fairly exotic winding machine, you can wind a layer of the conductor, then you can spin around it whatever, glass, Kevlar, carbon, Xylon. And the advantage is you can change the thickness, because you need your biggest reinforcement round about here, and also there are times when you need to change the material itself because you want to match elasticities, because you actually want to allow for controlled plastic deformation. So you need to choose a material that will let the copper, let's say you're using, bed into it. So using this process you can actually change your material and the thickness of material as you wind the magnet. And of course finite element modelling and analytical modelling is now getting very important to tell you how thick these layers need to be and what they need to be and where they need to be. That's a spare slide that I always carry with me. Well, you can reinforce as much as you like, but in the end it's when and not if the thing goes bad. This is a standard Clarendon pulse magnet reinforced with carbon fibre. So you can see there the carbon fibre. By the way, everything is impregnated with epoxy resin, so it's a fairly sophisticated composite. And there is also some carbon fibre internally. Not every layer, but there's some internal reinforcement. That's it, after saying goodbye to us at 63 Tesla. Quite a mess. It was wound from some 30 metres of copper steel, but it was reinforced by God knows how much carbon fibre, and that's it. It's just a jumble of shards, and made quite a noise as well, I seem to remember. when it went. And that's all in a day's work. Because the problem is you get fatigue. After so many shots, the material says, I've had enough, I want to go home, and it does. So you can understand safety is quite a big issue and all that stuff, but we won't go into that now, because that's a growth industry where I work. Okay, so we've had to turn our attention to another problem. For something like 14 years, I've been trying to persuade the neutron scattering community that they want to use high magnetic fields with the neutrons. Now, I don't know how many neutron scatterers there are here, users of ISIS or, you know, Hahn-Meitner or ILL or whatever, but using a high magnetic field for reasons I won't go into because I don't know is something they want to do. But the problem is, and of course they all want to use continuous magnetic fields, they all want it in as big a bores as possible, they all want to be able to get the neutrons in and out and scatter them and this and that. But the problem is, they've managed to get split. Damien, for example, has a very exotic split superconducting magnet in his laboratory, because that's what you need. Because you need a field in this direction or that direction, and the neutrons need to come in like this, and then you have to look at them being scattered over there, so you need a split magnet. But it's also very expensive real estate when you start taking splits out of solenoid magnets. And I'm not sure, I believe at ILL, or is it Hahn-Meitner, I'm not sure, they've managed to get something like 12 Tesla in a split superconducting magnet, which costs the Earth to run and all that. So what I've been saying to them is, well, why don't you think about using pulse magnets? Well, we can't use pulse magnets because, you know, you don't get many bangs for your buck sort of thing. You get so many neutrons and you lose half your neutrons and so on and so forth. Well, all that's true. But on the other hand, think of it a little bit like light. If you're taking a photograph in a very dim light, you have a long exposure. So pulse neutrons with pulsed magnetic fields with pulsed neutron sources, such as ISIS, might be worth looking at. I've been telling them for 12 years, and I've done the circuit. I've done ILL, Hahn-Meitner, Japan, everywhere, and at the end of the sessions, all they ever say is, yes, but we really need continuous fields, so they don't give me any money. Finally, about a couple of years ago, the people at ISIS said, well, all right then, you can have a miserable sum of money, go and see what you can do. And that's what we're doing. And what we're going to do is we're going to give them a milliseconds worth of 25 Tesla every second. Of course, they want 10 milliseconds worth 10 times a second and so on. So the negotiations go on. I mean, you know, talk about pay negotiations, field negotiations between us and the neutron community are just as complex. But finally they've agreed, yes, okay, because and the argument is this: 25 Tesla. It's not huge to us. It's not a huge field at all. You've just heard me airily talking about 90 and 100 Tesla and 70 Tesla and so on. But 25 Tesla, I'll explain why we want to keep that a little bit low, and it's still a considerable increase for the neutron people. So it's a good compromise. So that's what we're going to do. 25 Tesla, bit different, certainly for me. And the coil is going to look like this. Well, at least the simple version of the coil is going to look like this. This is a quarter of the coil, okay? So it's a vertical field. That's the bit you're looking at. There's a split. There's another bit. That's the bore of the magnet. Okay, so the idea is the field is in this direction, and the neutrons, I believe, and you can tell me anything about neutrons. I don't know anything about neutrons, but neutrons come in here. We need plenty of open space and slits and so on, so they can scatter it here or there or whatever. But that's the idea, and that's what we're looking at. But in order to get up to the field level we need, we have to use a big voltage, 45 kilovolts actually, which frightens me to death just the thought of it, but that's what we've got to do, okay. 45 kilo, and so we're going up to this sort of level. So we need a big conductor, and we need cooling channels in between, because we've got to get a lot of heat out of the system. We're going to use a setup like this. And what this is, the magnet is this inductance here. We charge up the capacitor bank, fire the magnet. When the voltage changes through this diode, we get the energy out of the magnet, store it in this flywheel inductance. So what we then have to do is we put this energy back into the magnet, but we top it up just a little bit to make up the ohmic losses. The alternative would have been a 500 kilowatt charging unit. And this is what you get. You get the magnet current, and then the voltage on the magnet at the end of the pulse is in fact just a little bit down, and that's the bit you've got to charge up. But instead of using 500 kilowatts, you only need about 50 kilowatts to make up that difference. And so it goes on. The idea of using 25 Tesla is that you're using a small, an over-engineered magnet and very much underrunning it, because we want to get the life out of it. We need hundreds of thousands of shots in order to get this exposure I was talking about. But a new problem for me is eddy current heating, because of the high repetition rate. And one of the frights we've had just lately is that in this region of the magnet we're going to get far too hot. So we've got to devise other ways of actively cooling these inner reaches of the magnet. Okay, condensed matter physics. It's condensed matter physics seminar. I haven't done that much hands-on condensed matter for quite some time, so I decided to appeal to one of my younger customers, and this is Dr. Paul Goddard, who showed me these amazing things. What we have here is what he calls magnetic Lego. It's a layered structure, not unlike high temperature superconductors, and by changing these various ions and materials in there, we can get these many different structures, and by using high magnetic fields we can examine the nature of the magnetism. And what you see here are various changes on the structure, and what we're seeing is the use of very low temperatures. In my abstract I say we talk about the B over T factor, which to me is a figure of merit in a condensed matter physics laboratory. And these measurements, these phase changes, these magnetic phase changes, are being seen as functions of magnetic field and down to temperatures of around about 100 millikelvin. Very elegant, very nice work. And that's going on in Pulse Magnetic Field Laboratory. Future, nearly at an end, Damien. Future, well, I don't know. I don't want to be pessimistic, but it's running up against the buffers thing. And this is where I want to appeal to condensed matter physicists, and you'll see why in a second. I think we will get 100 Tesla pulse before long at Tallahassee or Dresden, which is a brand new pulse magnet laboratory in Germany. I had the honour of being chairman of its external advisory committee until about a year ago, where they've got 50 megajoule capacitor bank, so if anyone's going to do it, they ought to do it. I think there will be a 50 Tesla hybrid magnet, probably at Tallahassee within 10 years. We will probably have 30 Tesla high temperature superconducting magnets, but I somehow don't think anymore. At Hahn-Meitner, I believe they're going for a 40 Tesla continuous setup. They're going to stick a hybrid magnet on the neutron beam at Hahn-Meitner. But for major advances though, it's a matter of materials. And to paraphrase Mr. Blair, materials and materials. And the reason I mention that, because I was telling Damien earlier, when I became a professor of condensed matter physics, a lot of people, my relatives for example, it wasn't the professor that impressed them, it was the condensed matter physics. It was just so outlandish. So to try and explain to them what that was, I just say, well, condensed matter CMP is really the physics of materials. And I happen to think that although condensed matter physics is often seen as prosaic, not particularly glamorous when you compare it with astrophysics and particle physics and so on, but I think it's the most economically, industrially, and actually socially relevant of the branches of physics for materials. Socially, you might say, socially relevant. Well, to illustrate that point, can I just introduce you, for those who haven't come across this character, his name is Onslow. He's the brother-in-law from hell of the aspirational hyacinth bucket, pronounced bouquet, and he's my hero and role model. Because he gets to slop around all day, lying in bed with his besotted wife Daisy, quote, "Onslow, why are you so attracted to women? It'll fade in time," he said. And he gets to eat crisps and drink beer and bacon butties, and he doesn't do a stroke of work by his own admission. "I'm bone idle and work shy." But who's the stupid one when you think about it? That's the way I look at it. However, he might be averse to physical exertion, but he likes to keep his mind alert. He's a philosopher, a man of the world. So I think it might be interesting in the last second of my talk just to take a little look at his reading matter. Thank you very much.
Okay, so we're open to any questions.
It's amazing what you can do with paint shop pros. Is that straight out of the series?
Straight out of television, that was taken off a videotape, yes. I know Paul Chaikin quite well. He was one of the authors, and I was so amused to see it that it was several years later when I became a professor of condensed matter. I said to my wife, "God, I wish I could get hold of a copy of that scene where he was reading." And by sheer luck, that weekend they repeated it. She videoed it, and I got our photographers to. That's what he was reading.
Are there any questions? Got time for just one or two.
I don't know whether it's a question.
Yeah.
But I mean, I've been looking around metals recently for an interesting alternative career I've got. But I noticed there were materials which contain tiny amounts of, say, alumina or zirconium in copper.
Yeah.
And these things incredibly change the yield strength and ultimate strength and retain all the conductivity properties. You'll know about it.
You're talking about grid copper, I think.
Exactly,
Yes. Yeah. Well, the trouble is, it's good, very good, but it's not good enough. It's still quite a weak material for our purposes. You maybe get 600-700 megapascal, something like that, which is twice as strong as copper. But we need 1 to 2 gigas for the sort of thing we do.
I believe they were touting you for accelerator work.
Yeah, oh yeah. I mean, I've got some and I've used it, especially if you use it in combination with the reinforcing fibres. It can be quite a useful material.
I have got a question. Is it very expensive?
Glycop?
Yeah.
No, actually. I mean, I can't really.
No, really, you're on the scale.
I mean, I quoted you my 26,000 euros for some copper niobium. It's nothing like that. It might be twice maybe the cost of copper. You can get it there. It's Höganäs. Höganäs is the company, and I think they actually make it in the States. It's a Swedish company, but it's a.
Any other questions from any of the students that are here? Well, time is moving on, so just to thank the speaker again.